Okay, guys, before we begin or before we continue talking about functions and graphing more functions besides the quadratic from last time, we got to take a little aside and talk about synthetic division. Okay, synthetic division provides an efficient process for dividing a polynomial by a binomial. Only works if you're dividing by a binomial. In other words, something with two terms, right, of the form x minus k. So here's a typical division process of some polynomial, right, a cubic polynomial being divided by a binomial. And here's the process. It's just like long division. With synthetic division, notice how a lot of these numbers are duplicated, and we have to keep our columns all straight. These are all x squared, these are all x cubed, these are all x's. So keeping that in mind, a lot of that stuff we don't have to rewrite. So all I'm going to use are the numeric parts. Okay. Now, if we have a missing term, just like in long division, we've got to fill it in with 0. So I'm going to just put up the 3, the -2, the 0, and the -150. Then I'm going to make myself a thing like this, a little bracket. Okay, and there's a couple of different things. If we're given the actual binomial, we've got to change the sign of the number. So I'd put a +4. If they tell me k equals, they've already changed the sign. Notice our format has a minus here. So when I pull the k out, I've got to change that sign. Okay, first step, we just bring that first number down. And then it's just a series of multiplying and adding in a zigzag fashion all the way across. So 4 times 3 is 12. And then we add these. 12 minus 2 is 10. 4 times 10 is 40. And then we add these. 4 times 40 is 160. And then we add these. Right? Notice here's the 3's. Right? Here's my answer. Here's the 10. Here's the 40. Okay. Oh, they left off part of this problem. Well, here's the remainder. They just didn't write it. Okay, so here's the remainder of 10. Okay, so notice the similarity. Here's my 12. Look, here's the 40's. I just had to write it once, though. Here's the 150 and the 160. Much shorter process, but now we got to remember how to put it back into a polynomial format because this really doesn't make any sense. So since I'm always going to be dividing by just one x, because that's the only time synthetic division works, it's always going to knock these exponents down by 1, right? If I divided this term by an x and this one by an x. So instead of starting with a cube, my variable part will be x squared. Okay, and then it'll go down in descending order. And this last term is always our remainder. So if I'm putting it back, I can say with a remainder of 10, that really doesn't make sense since we've got a polynomial. So if I'm putting it back, we'll do it like in the fraction format. So we'll put 10 over whatever we divided by, x minus 4. Okay, so just a lot shorter way to do division. And we want to be really good at this because in the next section, we're going to be doing synthetic division in every problem, in some problems, 4, 5, 6, 8 times. Okay? All right. So let's just practice that. All right. So first thing, we got to make sure that we don't have any missing exponents because if we do, we've got to put in that 0 placeholder, right? So 3, 2, 1, 0. I'm good here. To do my synthetic division, I just write up the coefficients of each term. Don't forget to change, well, I didn't leave myself much room there. Don't forget to change your sign since it's given me the factor instead of what k actually equals. Bring the first number down to get us started, and then just multiply and add all the way across. So -2 times 5 is -10. Adding, I get negative 16. Negative 2 times negative 16 is positive 32. Adding, I get 4. Negative 2 times 4 is negative 8. Adding these two, I get negative 10. Okay, now because this started out being a cube, my answer is going to be a square. So it's 5x squared minus 16x plus 4. And don't forget this last column always represents our remainder. So I've got minus 10 over x plus 2. Very nice, short, sweet process. And it's good because we're going to use it a lot. Okay, first step, check your exponents. 4, 3, 2, 1. Oh, it's got to go all the way to 0. So I need a placeholder here when I write up these terms. So 1, negative 1, negative 5, negative 3, 0. Let's double check. 4, 3, 2, 1, 0. All right, now what are we going to divide by? Right, negative 1. Bring the 1 down to get us going. Negative 1 times 1 is negative 1. Add these together. Negative 1 times negative 2, positive 2. Add these together. Negative 1 times negative 3, positive 3. Add these together. And negative 1 times 0, 0. Hey, look, this time I didn't have a remainder, right? I didn't have a remainder. So since it's a 4th degree polynomial that we were starting with, our answer will be a 3rd degree. So x cubed minus 2x squared minus 3x. Notice there's not a constant term and there's no remainder. Okay, so synthetic division. Okay? All right. Now, a couple of uses of synthetic division. One, we're going to use, just like I told you, in helping us solve the rest of our graph and solve the rest of our functions. But also, here's a nice little advantage. Now, here's the problem that we just did, right? That first problem that we did. And remember, we had, here's the same synthetic division process that we had, so we don't have to do it again because we already have that. But look at this. What this theorem is telling us is this remainder is actually the answer to evaluating the function at this value. In other words, so here's my function, right? Here's my function. So if I wanted to know what f of negative 2 is, what would we do? We'd plug it in. And so 5 times negative 2 cubed minus 6 times negative 2 squared minus 28 times negative 2 minus 2. And then we just evaluate, right? So this is 5. Negative 2 cubed is negative 8. Okay. Negative 2 squared is 4. And then I can go ahead and do this, negative 28 times negative 2, so that's positive, what, 56 minus 2. All right, just continuing to do our basic math. So here we have negative 40 minus 24 plus 56 minus 2. So here's negative 64 plus 56 minus 2. So finally, what do we have here? Negative 8 minus 2 equals negative 10. F of 2 is negative 10. Hey, look at that. That's what the remainder theorem is telling me. Now look at the difference in the math that we had to do to get the answer up here and the math that we had to do to get it in our traditional method. So this is a real handy thing to remember. Now when we're asked to, find f of, think about if we were asked to find, f of 3 on this, just adding a 3 or a 4, I'd have to cube that. These numbers would be dramatically larger. This wouldn't change very much. I'd just be multiplying by a 3 or a 4 instead of a 2. Okay, so really huge, really huge. Let's see if we can practice that. Yeah, that's what it's asking us to do. Okay, so here's our function, and it wants us to find f of -3. So I could plug in, but what a pain. I could use synthetic division though, so let's do that. 2. I got a missing place here. 2, 1, 0. So I've got to remember that. -1, don't forget your placeholder 0, 3, -4, -5. And I'm going to double check those exponents. 4, 3, 2, 1, 0. Great. Not missing any, goes all the way to 0. I want to find f of -3. Now notice it's already given us the number now, so I don't have to change that sign. Okay, it's given us that number. So bring the first number down. -3 times -1 is 3. Okay, add them. -3 times 3 is -9. Add them. -3 times -6 is 18. Add them. -3 times 14 is -42. Add them. So now I know that f of -3 equals -47. And I didn't have any difficult math at all. As difficult as it got was 3 times 14. Okay. Same thing here. Let's try this. 2, 1, 0. First step, check those exponents. None are missing this time. Oh, but look what it wants us to find. 2 plus I. But that's okay. It's okay. We know how to add and subtract and multiply complex numbers, right? So bring 1 down to get us started. 2 plus 1 is 1. 2 plus I times 1 is 2 plus I. Okay, so 2 plus I times 1 is 2 plus I. Remember, when we're adding complex numbers, the real number parts add and the imaginary. So this is really -5 plus 0 i's, right? So this would be -3 plus I. I've got to multiply these together. I might have to go over to the side to do that, or in this case down at the bottom, right? 2 plus I times -3 plus I. It's just our distributive property. So we wind up with -6 plus 2I minus 3I plus I squared. Remember, anytime we had an I squared, remember I squared is -1, right? I squared is -1. So this really gives us -6 minus 1, -7 minus I. Okay, so that's what I put here, -7 minus I. And once again, I don't have an imaginary part, so I just add the real number parts. So 1 minus 7, -6 minus I. F of 2 plus I is -6 minus I. Okay, so not bad, not bad. Okay, so that's the remainder theorem. So that's going to be useful. Try to remember that. Okay, now here's the whole reason we had to step aside and use this synthetic division. Okay, it's for testing potential zeros. A zero of a polynomial function is a number, right, where that equation equals 0. And those are the x-intercepts of the graph. We just did that on the quadratic functions. Remember, when we were trying to find our x-intercepts, we set that function equals 0 and factored it. Okay, so the remainder theorem gives us a quick way to decide if k is a 0 or not, because now we're going to have 3rd, 4th, 5th, 6th, 7th degree polynomials that we can't factor, right? Or, well, we can, but that's what we're about to learn. How do we factor something like that? Okay, so we're going to use synthetic division. And then if your remainder is 0, that is one of your x-intercepts. Okay, so that's what all this is saying. All right. So it says, decide whether this number is a zero of the function or not. I'm going to use synthetic division. 3, 2, 1, 0. All right, so I don't have any missing terms. Just put up your coefficients. And don't change the sign because it's already given it to us as the k, not x minus 1. If I wanted to put this back into my binomial, it would be x minus 1, right? They've already changed the sign. Bring the 1 down. 1 times 1 is 1. Add them together. 1 times -3 is -3. Add them together. 1 times 6 is 6. Because that's a 0, then yes, I found a 0, which is also going to be an x-intercept. We can call them roots. We can call them solutions. We'll talk about all that next time. But this is what I'm looking for. All right, what about this one? Whoops, we got a missing term there, so don't forget to put your placeholder. 1, 0, 1, -3, 1. Double check. 4, 3, 2, 1, 0. Once again, it's already given it to me as the k instead of in a polynomial form or a binomial form. So pull the 1 down to get started. -1 times 1, -1. Add them together. -1 times -1, +1. Add them together. -1 times 2, -2. Add them together. -1 times -5, 5. Add them together. Nope. So I would have to try another number, right? So this is why we're going to have to do this a bunch in the next section, over and over. We're just going to try them over and over and over until we get a 0. This one is not what we're looking for. So I want to be really good at my synthetic division. Let's do it one more time. Okay. All right. 4, 3, 2, 1, 0. Don't have anything missing. So 1, -2. Just put those coefficients up. Don't forget the sign in front of the number is part of that number. Okay. Complex number again, but that wasn't too bad, right? All right. Bring the 1 down to get me started. So 1 plus 2i times 1 is 1 plus 2i. Add them together. You only add the real number parts and the imaginary parts. So -1 plus 2i. All right, I might have to come down here and multiply that out. 1 plus 2i. All right, if I was smart, I'd rearrange that and recognize that it's not a perfect square trinomial, it's the difference of squares. Make my math really easy. In case we don't see that, we just, trudge along, do the same thing. So 1 times -1 is -1. 1 times 2i is 2i. 2i times -1 is -2i. 2i times 2i is 4i squared. And remember, every time we see an I squared, it's really -1. All right. Hey, look what happened. 2i minus 2i. See, remember from our complex conjugates? Okay, if I'd have written as 2i plus 1 and 2i minus 1, I could have done the shortcut. Okay, but now we've got -1 minus 4, because 4 times -1, so this is -5. Goes right here. 4 minus 5 is -1. So 1 plus 2i times -1 is -1 minus 2i. Adding these together, 2 minus 1 is 1. Okay, minus 2i. Hey, once again, this time it's real obvious that they're conjugates. So remember how we multiply these out. The difference is squares. Square the first one, make it a minus, and square the last one. 4i squared. But every time we get an I squared, it's -1. So this is really 1 minus negative 1. Not negative 1, negative 4, because I got a negative 4 right here times a negative 1. So 1 plus 4 or 5 again. Oh, and add them together? Yes. Look at that. We found even a complex solution using this synthetic division. All right, so hopefully you can see how hugely important this is going to be for us. Let me know if you have any questions. I'll see you guys next time.